All right, welcome everyone to AMAT 120. This is Applied Calculus A. This is our first lecture on section 1.1. We're going to talk about average velocity and instantaneous velocity. Okay, so to start off with, calculus is all about rates of change. And one of the simplest rates of change that we know about is velocity. Okay, so velocity is going to refer to the rate at which an object is moving. In other words, it's the rate of change in position over time. Okay, so a little bit of a physical or physics motivation here. Okay, so for an object moving in a straight line with a position function s of t, right? So s is the function dependent on time, the variable here. The average velocity of the object from t equals a, our start time, to t equals b, which is going to be our ending time, is going to be given by the following formula. So average velocity is equal to s of b, so this is the position at b, so this is our ending position, minus s of a, this is our starting position at time a. Okay, so the distance, or the difference between these two is going to give us the distance and how far it moved in that time period. And then on the bottom, we've got b minus a. So this is just going to be your end time minus your start time, and this is going to give us the duration or the time period that we're dealing with here. Okay? So let's suppose we went and we plotted this. This blue curve might be our position, right? So this is the object's position in space. It's kind of going backwards and forwards over time. And here is our starting point, our starting time A. This is its ending point at the end of our interval, which is at time B. This is its position at time A. And then this is its position at time B. Okay, so the average velocity, all we're really doing is, in a sense, we're calculating the slope of the line between these 2 points. Okay, so this is the point a comma s of a, so time a comma its position, time b comma its position at time b. Okay, so just like we're saying here, so the average velocity is really just the slope of the line between these 2 points. And the slope of the line formula, if you remember, is y2 minus y1 divided by x2 minus x1. That's exactly what we're doing here. So we're taking y2, which is sb, minus y1, which is sa, and divided by x2, which is b, minus x1, which is a. Okay? So this is going to give us the average velocity. Let's take a look at an example. All right, so suppose you have a baseball, you throw it straight up in the air from the top of a 10-foot tall platform. Its position in feet is given by the following function. S of t is equal to negative 16t squared plus 20t plus 10. All right, so first of all, what's the ball's average velocity over the time interval from t equals 0.2 to 0.5 seconds? Okay, so we've already got our average velocity formula, so let's go ahead and try to plug in the values that we have here. So we're going to start with y2, which is going to be its position at 0.5 seconds, minus y1, which is the position at 0.2 seconds, our starting time, divided by 0.5 minus 0.2, right? So that duration of time that we're dealing with. And we're going to go ahead and now evaluate our function at each of these time periods, or time points. So we're going to plug in 0.5 first in for t in our function. We're going to evaluate that. That's what we're subbing in here. And then we're going to do the same thing with 0.2. We're going to substitute that into our function everywhere we have a t. Okay, so we're just going to simplify that algebraically. And you see that that comes out to 8.8 feet per second. Okay, so just by calculating essentially the slope between these two time points, we can calculate the average velocity. So on average, how quickly is the object moving between these 2 points in time? Okay. We can try now calculating the average velocity for a different duration of time, right? So now from t equals 0.5 to t equals 1 second. Okay, so we're going to go ahead and use the same formula, but this time our endpoint is at 1 second, and our starting point is at 0.5 seconds. Okay, but it's exactly the same process. We're going to plug in these new time points for t in our position function. We're going to subtract them in our denominator. You can go ahead and simplify that algebraically, and you're going to see that this time we get -4 feet per second. Okay, so initially we got a positive value, now we're getting a negative value. So let's think about why that would make sense first. Okay, so if we're throwing up a ball from this platform at our initial sort of duration in time between 0.2 and 0.5 seconds, we might calculate positive 8.8 feet per second as the ball is going up. Okay, and then on our second duration from between 0.5 and 1 second, we're now going to be catching the ball coming back down, and that's why we got a negative velocity. So later on in this sort of parabolic arc, which is what's given by the function that we're using for s of t. Okay, that's just a quick diagram for making sense of what we're talking about. So that's average velocity. Now let's think about an alternative formula for average velocity. So again, we're starting with average velocity is equal to s of b, which is the position at time b, minus the position at time a, over b minus a. So this is our full duration in time between points a and b. But now, instead of thinking of b as its own separate point of time, what if we think of it as our starting point a plus a little change? Right? So initially we had something like a is equal to 0.2, b is equal to 0.5. We could just have represented the 0.5 as 0.2 plus 0.3, right? So 0.3 is a little bit of change in time, right? That we're tacking on to that starting point. But we're just going to do this algebraically. So we're going to represent that little change as h. Okay, let's see. This has some benefits to it as well. This is going to help simplify our formula a little bit. Okay, so if we go ahead and we do that, we substitute a plus h, so our starting point plus that little change in time, that little interval, this is what the formula is going to become. So we're going to replace b with a plus h. So now you've got s of a plus h minus s of a in the top, a plus h minus a in the bottom. And the bottom, that is going to cancel out. Those a's are going to cancel out. We're just going to be left with h. Okay, so our new sort of simplified average velocity formula in terms of a singular point in time, a, and some incremental change, h, is going to be s of a plus h minus s of a over h. Okay, we're going to see why this is useful in a second now. So thus far we've been talking about average velocity. Now let's talk about instantaneous velocity. What is that? Okay, so while average velocity is giving us information about a change in distance over some duration of time, right, from A to B, it doesn't tell us anything about the velocity at a single point in time, right? So every single point in time, some object has some instantaneous velocity of how fast it's moving right at that instant. We haven't really calculated that, right? Because we're using two different points in time to estimate this with sort of a slope, okay? So that's where instantaneous velocity, this new concept, comes in. It's the velocity at that single instant in time, okay? To find it, we can start off, at least, by looking at a sequence of average velocities over smaller and smaller time intervals. And we can see if we can find where they're going to converge. What value does it seem to be approaching as that h gets smaller, right? So that we're denoting that time interval now by h. Okay, so in other words, we want to see what happens as h is getting smaller and smaller. Okay, so let's look at an example and see how this works. All right, so now we've got example 2. Consider the following function for the position of a moving object at time t. So our position function s of t is given by 32t squared plus 100, and this is in meters. Okay, we want to find the instantaneous velocity at t is equal to 10 seconds. Okay, so let's see how we can do that. Let's start by calculating the average velocity formula using that general h that stands in for that duration. Let's see what that looks like. So the average velocity is going to be s of 10 plus h at some general ending time minus s of 10 at our starting point divided by h. So let's go ahead and plug in 10 plus h and 10 into our position function, 32t squared plus 100. So we're substituting 10 plus h in here for t, 10 here for t. Next step, we can go ahead and expand this. And we're just doing some simplification. So all I've done is expand this. This is a plus b squared, and I'm using the a squared plus 2ab plus b squared formula here. So we go ahead and next step, distribute that 32, see if we can combine like terms. Our constants are going to cancel out. We're going to be left with only h terms because everything in the numerator has an h, and we can divide out with that h in the denominator. We're going to be left with 640 plus 32h. This is our simplified formula for average velocity. Okay. Now this simplified formula is what we're going to try to use to calculate the average velocity at multiple time durations, right? So multiple h, remember, is a duration of time. It's the time between point A and point B, some length of time. So let's make ourselves a little bit of a table over here, and let's see what happens as we calculate h at different lengths. So we start off with h being 1 second. You're going to plug in 1 for h over here into our simplified formula, and you'll get that the average velocity over that 1 second duration between 10 and 11 seconds is 672 meters per second. Now, if that h shrinks to 0.1, now we plug in 0.1 for h, again, the duration. So now this is between 10 and 10.1 seconds. The average velocity has dropped significantly to 643.2 meters per second. Okay, we can do the same thing again. We now make it 0.01, so now we're talking between 10 and 10.01 seconds. This is the time span we're talking about. The average velocity on that time span, 640.32 meters per second. And if we get even smaller, 0.001 seconds. So now we're talking 10 to 10.001 seconds. That's the duration of time we're talking about. We get 640.032 meters per second. So we can clearly see that as h gets smaller and smaller, as it approaches 0 seconds. And why do we want it to be 0 seconds? Because we want, if we have a duration of 0 seconds, it's no longer the average velocity, it becomes instantaneous velocity. Okay, that's the velocity at exactly 10 seconds. 10 seconds and nothing else. Right? 10 seconds is the start point and the end point. That's why h is 0. The duration is nothing. That's what an instant is sort of defined in this math. And then we can see what's happening here is as we get to that duration of 0, the average velocity is approaching 640 meters per second. That's what it appears to be approaching here, right? So we're getting closer and closer to that 640. Okay, so what we would conclude in this case is the instantaneous velocity at t equals 10 seconds of this object is 640 meters per second. Okay, so we've done that using average velocities at multiple durations as an estimate. Now, I want to note that in this case, we could have even gone a step further. We could have actually just plugged in h is equal to 0 and just done the same math. 640 plus 32 times 0. We would have gotten 640 right there. Okay, and this actually would have given us quite literally the instantaneous velocity. Okay, in this case. But this is not going to work in general if h does not cancel out from that denominator, right? So we had this h term in the denominator. This is going to be an obstacle in a lot of different formulas and functions and things like that. It's not always going to cancel out so nicely. So that's why this procedure of approaching 0 but not actually plugging in 0 exactly works for all of these general cases. Okay, so in this case, yes, you could have just plugged in 0 here, but if this h doesn't cancel out, say you had a different function where we couldn't cancel it out, that 0 in the denominator would be a problem. Okay, so just want to make that note. So for example, if we had something like the average velocity was given by this formula, 32h squared plus 10 over h, you can't plug in 0 here now. But you can still use this approach. So you start with 1, go to 0.1, 0.01, 0.001, so on and so forth, and you can see what you're approaching.